Welcome back to Physical Science 101. This time we're going to be talking about balanced forces, which are covered by Newton's first law, and force pairs, which are covered by Newton's third law. We'll start with Newton's first law and balanced forces. Now remember that Newton's second law stated that an unbalanced force changes an object's velocity. Newton's first law is the opposite of Newton's second law. So if the forces are balanced, then an object's velocity will not change. Or we can say that the other way around. If an object's velocity is not changing, then we know that all forces must balance. So let's think about Newton's first law the way that you might have learned it in high school. In high school you might have learned an object at rest remains at rest, and an object in motion remains in motion at constant speed in a straight line unless it is acted on by an unbalanced force. Let's unpack that. An object at rest that remains at rest, so in that case the object's velocity is 0 and stays 0. So it has 0 velocity and it stays 0 velocity. That is, an object's velocity is not changing. The second part is also velocity that's not changing. An object in motion remains in motion at constant speed in a straight line. So notice that both of those are necessary for velocity to be constant. We have to have a constant speed, which means the speed is not changing, and it has to be moving in a straight line, which means that the direction is not changing. So both parts of that statement describe an object whose velocity is not changing. An object at rest remaining at rest, or an object in motion that remains in motion both at constant speed and in a straight line. So that first half of the statement means that the object's velocity is not changing. So if an object's velocity will not change unless it is acted on by an unbalanced force. So if an object's velocity is not changing, therefore the force is balanced. So if an object's velocity is not changing, then all forces must balance. That is Newton's first law. If an object's velocity is not changing, then all the forces on that object must be in balance. Now the situation where all the forces balance and an object's velocity doesn't change is called equilibrium. Equilibrium, that implies a balance. So if we have balanced forces, we have equilibrium, and Newton's first law applies. Now here's the key. Equilibrium can be either static or dynamic. Static means that the object is at rest and remains at rest, and dynamic is that the object remains in motion at constant speed in a straight line. Okay, so the first two halves of that statement are static and dynamic equilibrium. Okay, so remember Newton's first law as an object at rest remains at rest. That's an object in static equilibrium, or an object that remains in motion at constant speed in a straight line. That's an object in dynamic equilibrium. If you have either of those cases, then your forces are balanced. Let me do a little demonstration of that to drive that point home. Here is our box that we're familiar with from last time. And let me add my mannequin applying a force. So now my mannequin is applying a force, and let's make that force 25 newtons. So you can see that we have an applied force of 25 newtons, and the box is at rest and remaining at rest. So the things we know are that we are applying a force of 25 newtons and the box is at rest and remaining at rest. Therefore, we know that there has to be a balancing force. That force would be friction. So our applied force of 25 newtons is balanced by a friction force of 25 newtons so that the box remains at rest. So it's at rest and remains at rest. This would be the case of static equilibrium. Let me push a little harder. I'm going to push a little harder and the box remains at rest. So the box is still in equilibrium. So now I'm pushing, my mannequin's pushing with a force of 50 newtons. The box is still in static equilibrium. It's not moving and it stays not moving. So we know that the force is balanced. Therefore, we know that there has to be a friction force balancing it. Okay, so the box is in equilibrium. It's at rest and remains at rest. We know that if I keep pushing, eventually we will not have equilibrium. Okay, now we do not have equilibrium. My applied force is not balanced by the friction force, so the box is accelerating. Okay, so this is not equilibrium. The speed is changing, the box is accelerating, but now I'm going to reduce my force until we're back in equilibrium. Okay, so we have a friction force of 94 newtons and an applied force of 94 newtons. Therefore, we are back in equilibrium. But it's not static equilibrium because the box isn't at rest. Now the box is moving, but it's moving at constant speed. Take a look at the speed. Notice that the speed is not changing. It's moving at constant speed and it's moving in a straight line. So the box is moving at constant speed in a straight line. So the box is in dynamic equilibrium. Therefore, we know that my applied force of 94 newtons must be exactly balanced by a friction force of 94 newtons. So the box is moving at constant speed in a straight line because all the forces balance. If the forces are even slightly imbalanced, let me apply one more newton of force. Okay, I'm going to apply a force of 94 newtons against the friction. I'm going to apply a force of 95 newtons against the friction force of 94 newtons. So now we have an unbalanced force of 1 newton in the direction of the box, and notice that the speed just increased. It was 18.8, now it's 18.9, now it's 19.0. It's not increasing very quickly because we don't have a very big unbalanced force, but it is increasing. We have an unbalanced force of only 1 newton, so the box has a small acceleration, and you know that. You know that the box isn't moving at constant speed because that speed gauge is changing. It's 19.4 now, 19.5, 19.6, okay? So the box is not moving at constant speed. So that 1 extra newton of force is enough to accelerate the box, is enough to change the box's speed. Now let me reduce my applied force back down to 94, and now the box is moving at constant speed. I can leave it there and the speed of the box will not change. Let's give it a little bit of time. Okay, by this time we should have seen something. Okay, that box is still moving at 19.8 meters per second. Steady 19.8 meters per second. It's moving at constant speed. Let me reduce my force once more so that I'm only applying 93 newtons. So now I'm applying 93 newtons of force against a friction force of 94 newtons, and we have an unbalanced force opposite the motion, so the box is no longer in equilibrium again. Notice the speed slowly decreasing. We're down to 19.5, 19.4, 19.3. Okay, so you see that even that 1 newton of unbalanced force means that the box is no longer moving at constant speed. If I want the box to move at constant speed, then the forces have to exactly balance. So I've increased my force back up to 94, and now that speed will be rock steady because the forces are now balanced, which means that the box is in dynamic, meaning moving, equilibrium. Okay. Now I'm going to do something here that I can't do in a laboratory or in practice. I guess we could do something in a laboratory, but nothing that I have access to right now. I'm going to get rid of the friction on the box. I'm going to reduce the friction on the box to 0, and I'm going to reduce my force to 0 as well. And I'm going to do that first. I'm going to reduce my force down to 0. So I'm applying 0 force, but I'm also going to get rid of the friction. So now I've gotten rid of friction. There's no friction force, and there's no applied force. So now there are no forces on the box. The box is back in equilibrium. The box is back in dynamic equilibrium, and keep your eye on the speed. You'll notice that it is still moving at constant speed. It's moving at constant speed because all the forces are balanced. There is no applied force, there is no friction force. We have 0 balancing 0. Okay, so if I were to push in this situation, even with 1 Newton of force, that box would speed up. Okay, but before I do that, just take a look at that box moving at constant speed. That speed is rock steady. It's not going up, it's not going down. It is continuing to move at constant speed because the force is balanced, because the box is in dynamic equilibrium. Okay, I'm going to have my little mannequin give us 1 Newton of force. The mannequin is barely pushing with 1 Newton of force. Notice the speed has already changed. It went from 13.8 to 13.9 to 14, 14.1. So even 1 Newton of force, if there's no friction force, will cause that box's speed to increase. Okay, so let me get rid of that. Okay, so the box is in dynamic equilibrium, no friction, no applied force. It is still moving at constant speed. If I bring friction back, and I want it to move at constant speed, then I have to once again apply a force to exactly balance the friction force. So if the forces are exactly balanced, then the box is once again moving at constant speed. So moving at constant speed means the forces balance. Okay, I have a few questions for you, a few multiple choice questions for you. The first is, an object moving without opposing friction or other opposing forces will A, still need a constant applied force to keep it moving at a constant speed, B, need an increasing applied force or it will naturally slow and then come to a stop, C, continue moving at constant speed, or D, undergo a gradual acceleration. Now think about the demonstration I just showed you and come down on a definite answer here. Okay, an object moving without opposing friction. So remember the demonstration when I got rid of friction, if it were moving without opposing friction, it continued to move at a constant speed without the mannequin pushing on it. If the mannequin pushed on it at all, then the box would either accelerate or decelerate. Okay, the box, if the mannequin applied any force at all to it, the box would accelerate if there's no friction. So the box was moving without friction at constant speed, and it kept moving at constant speed without any other applied forces. So the correct answer is an object moving without opposing friction or other opposing forces will C, continue moving at a constant speed. That's the box on the ice without the mannequin pushing on it. Okay, another question. You are moving a grocery cart at constant speed in a straight line down the aisle of a store. For this situation, the forces on the cart are A, unbalanced in the direction of movement, B, balanced, C, equal to the force of gravity acting on the cart, or D, greater than the friction forces opposing the motion of the cart. Okay, so once again, think about this, come down on a definite answer, but think about the box, this time with friction. Think about the box with friction, and think about the box with friction moving at constant speed. What were the forces on it? Okay, come down on a definite answer. Okay, remember the box with friction moving at constant speed had the forces balanced. Whatever the friction force was, the mannequin had to push with exactly the same force for the box to continue moving at constant speed in a straight line. So an object moving at constant speed in a straight line is in dynamic equilibrium, which means that the forces all balance. So the correct answer is, you are moving a grocery cart at constant speed in a straight line down the aisle of a store. For this situation, the forces on the cart are B, balanced. Okay, one more question. You are outside a store, moving a loaded grocery cart down the street on a very steep hill. It is difficult, but you are able to pull back on the handle and keep the cart moving down the street in a straight line and at a constant speed. For this situation, the forces on the cart are A, unbalanced in the direction of movement, B, balanced, C, equal to the force of gravity acting on the cart, D, greater than the frictional forces opposing the motion of the cart. Okay, once again, pause, think about it, come down on a definite answer, and then continue when you're ready to hear the answer. Okay, in this case, I'm just going to focus in on moving in a straight line at a constant speed. That is the critical part of that statement. The cart is moving at constant speed on a straight line, moving in a straight line at constant speed. That's all you need to know that the answer is, if an object is moving at constant speed in a straight line, then all of the forces are B, balanced. Okay, let's talk about Newton's third law. Newton's third law deals with what we call force pairs. Now, why is that? The reason for that is that Newton's third law states that a force, so any force, is an interaction between two objects. So a force is always an interaction between two objects. Furthermore, each object feels the same amount of force, but in opposite directions. So when two objects interact, they each feel the same amount of force, but in opposite directions. And that's true of every force. For every force, you have to have two objects interacting, and each object feels the same amount of force in opposite directions. So another way of saying this is, for every force, there is an equal and opposite force. You may have learned Newton's third law as, for every action, there is an equal and opposite reaction. When Isaac Newton used the word action, he meant force. So what Newton meant by action is what we now call force. That terminology has changed in the 300 years since Newton wrote that statement. So a better way of saying Newton's third law is, for every force, there is an equal and opposite force. And what you should take away is that forces always occur in equal and opposite pairs between the objects that are interacting. Let me give you a demonstration of that. Okay, let's demonstrate the importance of Newton's third law. Here I have my skateboard, and I am going to simply push off of the ground to go forward. Okay, now let's think about what happened there, and let's think about forces. when I push on the ground, I push backwards. So my foot pushes backwards. I am pushing the ground backwards. What is the force that makes me go forwards? It is the Newton's third law, equal and opposite force from the ground on me. I am exerting a force on the ground backwards. The ground, therefore, exerts an equal and opposite force on me forwards. So the force that makes me go forwards is the force of the ground on me, not the force of me on the ground, not my push. My push is pushing the earth backwards. What's pushing me forwards is the earth. The earth is pushing me forwards because of Newton's third law. So I am pushing backwards on the ground, therefore the ground is pushing forwards on me. So I'm pushing backwards on the ground pushes me forward. So the force that makes me move forwards, the force that accelerates me forwards, is the force of the ground on me because of Newton's third law. Let's demonstrate that a little bit more. Okay, I'm going to take this board that's on wheels, okay, this platform on wheels, and I'm going to push off of that. Okay? So instead of pushing on the ground, I'm going to push on the platform. Okay? What happened there? I pushed on the platform accelerated backwards. My force on the platform gave the platform an acceleration backwards, mass times acceleration. The platform also pushed on me, okay? But I have a large mass. So the platform and I exert equal forces on each other, but the platform has a small mass compared to me, so it has a large acceleration compared to me. I have a large mass compared to the platform, therefore I have a small acceleration compared to the platform. So which is almost zero. As a matter of fact, I didn't go forward at all, hardly any forward acceleration. So let's show that again. So I am pushing on the platform, equal forces. The platform has a small mass and a large acceleration. I have a large mass relative to the platform and a small acceleration. So here we go. My force is backwards. It's the forward force of the platform, which is all that would accelerate me forwards. So if I really do want to accelerate forwards, I should push off of something with more mass. So let's try the ground this time. Now I'm pushing on the entire Earth. The entire Earth has an enormous mass compared to me. So the Earth has the large mass, small acceleration. I have the small mass and larger acceleration. So now you can see what you might not have seen before. What's pushing me forwards when I push off of the ground is not my force. The force pushing me forwards is the Newton's third law reaction to my force. I exert a force on the ground backwards. The ground exerts an equal and opposite force on me forwards. Okay, so there you see Newton's third law in action. Before we go, I have a couple of more multiple choice questions for you. The first one is, which feels a greater force? A 0.04 kilogram golf ball or the 0.2 kilogram head of a golf club when the ball is hit from a golf tee? Possible answers are A, the ball feels a greater force, B, the head of the club feels a greater force, C, both feel the same force but in opposite directions, or D, the answer depends on how fast the club is moved. So once again, think about it. Pause, think about it, come down on a definite answer. The thinking about it is the important part. The thinking about it and definitely choosing one is important. So think about it, and then when you're ready, unpause and I'll talk you through this. Okay, the correct answer is that both feel the same force but in opposite directions. That's answer C. And why is that? That is Newton's third law. Newton's third law says a force is an interaction between two objects. In this case, the two objects are the golf ball and the golf club. That's our two objects. They're interacting. They feel equal forces in opposite directions, but equal forces is the important part here. So both the golf ball and the golf club feel equal forces in opposite directions. So that's C, both feel the same force but in opposite directions. Okay, one more question. A similar question, but slightly different with a different point. And this one is, which has a greater acceleration, a 0.04 kilogram golf ball or the 0.2 kilogram head of a golf club when the ball is hit from a golf tee? So now this is asking about acceleration. A, the ball has a greater acceleration. B, the head of the club has a greater acceleration. C, both have the same acceleration but in opposite directions. Or D, the answer depends on how fast the club is moved. Okay, once again, think about it. This is similar to the last question, but slightly different with a different point. So think about what that different point may be. And then pause, think about it, come down definitely on an answer, and then unpause when you're ready. Okay, now we're talking about acceleration. And remember that acceleration is equal to the unbalanced force divided by the mass. Both the golf club and the golf ball feel the same force. So the force is the same for both of these. They feel the same force, the same amount of force. The amount of force is the same for both of them, but this time they have a different mass. Okay, and mass is in the denominator. So if we divide by a bigger number, we'll get a smaller acceleration. If we divide by a smaller number, we'll get a bigger acceleration. So the one that has the smaller mass will have the greater acceleration for the same force. So smaller mass, same force, gives us the greater acceleration. So which one has a smaller mass? The golf ball. So the golf ball has the smaller mass with the same force, so the golf ball has the greater acceleration. So the correct answer this time is A, the ball has a greater acceleration. Okay, that is the end of this lesson. We'll come back next time with the final lesson from forces from Unit 2. And until then, think science.